So I would hope that by now you've looked at Lab 5 and realized that your job is going to be to do some hand optimization of y86 code. So this is going to be a brief video to show you how to tackle that kind of problem. So let us begin with a fairly simple program that is simply summing up the elements of an array. And in this case, I am signaling the end of the array by putting a sentinel value or a 0 at the end of the array. So our job is to iterate through the array, sum up all the values. And here's some y86 code that does that. And what we're going to do is go hazard hunting, so figure out what obstacles there are to this getting its best CPI, and then given those obstacles, figure out ways to mitigate them. Let us assume that we're doing forwarding and we're doing branch prediction. So the first question is, where might we stall? And let's look for data hazards. So we start going through the code and we look at IR move queues and XOR, and those are all ALU operations. And we know that with forwarding, they don't stall. And then I see a pesky memory operation. And I say, ooh, okay, that's writing something into RDI. And right after it, we're using that. So that's clearly going to be a problem. So we have, every time we go through this loop, we would pay one stall cycle between the MR move queue and the AND queue. And we're going to go through this loop 5 times. So that's going to cost us 5 cycles. Okay, do we have any other data hazards? We keep going. These are all ALU operations. So no other data hazards. Next up, we need to look for control hazards. So we have an unconditional jump. That doesn't give us any problems. But we have this conditional jump, the JE done up here. So could that be a problem? Well, it's a conditional. We're doing a prediction that says always taken. So on every iteration, we're going to pretend to jump to halt, and we're going to pay 2 cycles when that's wrong. So in fact, every time through that loop, except the last one, we're going to have predicted incorrectly. So that's unfortunate. We're going to pay 8 cycles there. So now the question is, what kind of CPI do we get for this program? So if you count all the instructions, or you could run this in the simulator, you'll find that there are 31 sequential instructions. And now when we compute CPI, we find that it always takes 4 cycles to fill the pipe. And then we computed that we're going to have 13 stalls. So we get a total of 48 cycles for our 31 instructions. So we're getting a CPI of about 1.5, which is not awful, but it's also not very good. So the question I want to start with now is, can we do better? Can we rearrange the code to make things better? So let us remember what the first problem was, right? The first problem was that we have a stall every cycle between the MR move queue and the AND queue. So how could we get rid of that? Well, is there useful work that we could put in the stall? And I might claim that there is useful work. So we have an add instruction down here that doesn't depend on RDI. Now, we only have to do that add if we're going to continue looping, but we're going to continue looping 4 times and only stop once. So maybe it's okay to put it up there. So what if we move this add up between the MR move queue and the AND? What would that do to our CPI? Well, we're no longer going to stall for those 5 cycles. 4 of them we're going to be doing useful work. And 1 time we will have done an add that we didn't actually need. So that seems like a win. So we could do that. So let's do that. So now we've moved the add up here. Here's our AND. And next up, let's see if we can do something about our branches. So notice, first of all, that we have 2 different jump instructions here. We're doing this unconditional loop back to the top, and then we're also doing this conditional jump to check for done. So is there a way that we could get rid of one of those jumps? So you might remember that looping constructs often put the loop check at the bottom. So could we change that conditional jump, that unconditional jump, to be the condition that says branch back? And if we were able to do that, not only would we improve our branch prediction performance, but we would just get rid of this other jump instruction, right? We would never need that one. So this seems like a good strategy. So if I want to change this last jump to be conditional, and we want it to predict true, to loop back, then what we want to do is we want to change it to be a not equal, right? So when that value wasn't 0, then we want to loop back. Oh, but wait a minute. In order to have a conditional there, where's the instruction that's going to set the condition codes? Well, it's back up here. That was that and Q instruction. So we're going to have to move that so it's right before our conditional jump. So if we do that, then when we rearrange things, we get rid of the JE done. And now we have our 2 add instructions first. Then we'll do our test instruction, the ones that's going to check to see if RDI is 0, and then we're going to loop back. And so now the question is, have we improved performance? Because now, every time through the loop, we're going to execute all 5 of these instructions. So that's 25 instructions right there. But it turns out that there's only 25 now because we removed a jump. 3 is 28, and the halt is 29. So we actually went from 31 instructions that we were executing before to 29. So we've reduced our number of instructions, and we've reduced our number of cycles. We're going to lose 2 cycles the last time through because we're going to predict that we're going around to the loop when we don't. But those are the only wasted cycles, and then we end up paying 4 instructions to load the pipeline. So now we have 29 instructions in 35 cycles, and we've reduced our CPI to 1.2. So these are the kinds of optimizations that you're going to have to look for in Lab 5 to get the kind of performance that you want. All right, well, I look forward to seeing what you do with that.